Right, this is the probably the first of several videos on Group 7 elements. It's suitable for IGCSE chemistry specifications, and when we're doing this video, what I'd recommend is you print the slides out from the video and then annotate them as we go on. I'd also recommend that you have a periodic table in front of you as well, and you can annotate that. The periodic table is the only visual aid you'll get in the exam, and it's important that when we're talking about reactions to do with elements in the periodic table that you have that in front of you while we're doing this. So let's get started. Group 7s are often referred to as the halogens. Now halogen, the word comes from a Greek word which means salt making, and the halogens, the group 7 elements, are found here in the periodic table. They're in group 7 because they all have 7 electrons in their outer shell. So if an exam question asks you for the electronic configuration of one of these elements, you know that the last shell has to only contain 7 electrons. Now, it's important that you know what the halogens look like, and the 3 halogens that I'm going to talk specifically about in this video are chlorine, bromine and iodine. Fluorine at the top, we don't tend to talk about that much, but it's important that you can predict some things to do with fluorine and astatine, which is at the bottom of the group, using the trends that we're going to talk about now. You need to know what the elements look like at room temperature. So chlorine is a green gas, bromine is a reddish brown liquid, and iodine is a grey solid. You should also know what these halogens look like when they're dissolved in water. So if we dissolve chlorine in water, we produce chlorine water, very originally named, and that's colourless. When we dissolve bromine in water, we produce bromine water, and it's a bit like dissolving a concentrate of orange squash in water. It goes from being a strong brown colour, orange squash isn't brown, but you get the point, on diluting a brown colour you get orange. And iodine does something slightly strange. It's normally a grey shiny solid at room temperature. You dissolve it in water and it actually turns brown, and there's a strong probability that some of you will have used iodine as an antiseptic on cuts. I know when I fell off a motorbike a long time ago that they put iodine on the cuts on my arm, and it was an iodine solution, and it stung like fury, but my arm was left covered in these sort of brown stains. So you need to know these colours. You should probably also know the colours of them when they're dissolved in a non-aqueous solvent. So instead of dissolving it in water, dissolving it in, say, toluene, an organic solvent. Now chlorine and bromine dissolved in an organic solvent have the same appearance, but iodine doesn't. When you dissolve iodine in an organic solvent, it turns purple, a beautiful purple colour. So that's slightly odd, isn't it? That iodine is grey when it's a solid, it's brown when it's in water, and when it's in an organic solvent, it's purple. So, what should we learn from this? Well, trends, boiling and melting point. So as you go down the group, the boiling and melting points, well, what do they do? Okay, we go from gas to liquid to solid, so the boiling and melting points increase as you go down the group. And we're going to look at why in a moment. The colour. Now the colour actually darkens as you go down the group, and you can see it probably best when they're dissolved in water. Colourless orange brown, and so if we're predicting the colour of astatine, well, actually I've never seen astatine, but it would be a dark grey, black solid. If we're predicting what fluorine would look like, well, the chances are it's going to be a gas, and it is a gas, okay, because as we go up the group, the boiling and melting points decrease. So fluorine would be a gas, and it would actually be colourless. So as we go down the group, the boiling and melting points increase and the colour darkens. You also need to know the test for chlorine. And to test for chlorine, we'd use a piece of damp litmus paper. And if you put chlorine with damp litmus paper, it bleaches it. It goes white. So a 2-mark question would be, describe the test for chlorine, and it would be, put a piece of damp litmus paper in and it bleaches it. Notice that's the test for chlorine, that's not the test for chloride. Those are two different things, and I'll explain that in a little bit. It's quite interesting, bubbling chlorine gas, bubbling that green gas over some brightly coloured flowers, a red geranium for example, and you put the chlorine gas over the red geranium and it takes all the colour out of the petals. So if you've got a lovely bright red geranium, it turns the petals white, which is quite interesting. So why does the boiling point of the halogens increase as you go down the group? Now, here's a diagram of 2 fluorine molecules. So that's F2 and that's F2. And here's a diagram of some iodine molecules, I2, I2 there. So that's a fluorine atom, that's a fluorine atom. F, I. Now, when you're boiling something like fluorine or iodine, you are not breaking the covalent bond between the atoms. That bond remains the same. All you're doing is taking one molecule and another molecule and moving them further apart. You're pulling the 2 molecules away from each other without breaking the bond between them. And the thing that sticks the molecules together are forces. So the forces would occur between the molecules in this area and in this area here. And those forces between the molecules are called intermolecular forces, okay, between the molecules. So the stronger the forces are between the molecules, the higher the boiling point of the halogen will be. And if you've got a nice small molecule like fluorine, maybe if I draw it out like this, imagine here's your fluorine molecule, like this, and like this, okay, and let's change colour, and we've got our intermolecular forces occurring between them. There's only a small surface area between them for these forces to interact, small surface area. Iodine is bigger. There's my iodine molecule, 2 iodine atoms bonded together. So in iodine, you've got a much bigger surface area for those intermolecular forces to act upon. So the intermolecular forces between the iodine molecules are stronger than those between the fluorine molecules, so you need more energy to separate the molecules, therefore a higher boiling and melting point. So that explains why as you go down the periodic table, the melting and boiling points increase. And I think I'm going to pause there, and that will be the first part of the video.